Can folks in the chat hear me okay? Thank you. Okay, so as always, don't forget the seating survey, section 3 today. Upcoming deadlines, we have our Piazza homework due on Friday. On Sunday is the usual Piazza participation cutoff. And Tuesday of next week, the guided inquiry small group activity number 4 will be due. I will have that up this afternoon. The only thing I'm waiting on for that is going through the previous comments from the small group activities and reassigning people to new groups in cases where the group dynamic was not working well. So I'm going to do that this afternoon, and then I will release the activity to everyone. Do we have any logistical questions before we get on to content? That's looking like a no. Okay, so we spent Monday and Tuesday doing the same thing both days, which was the introduction to this week's material, a set of sort of detailed aspects of acid-base behavior, and then buffers being the main topic after that. So since last Thursday, there have been quite a few Piazza questions that have come up as muddiest points that cover a lot of things having to do with acids and bases. So I just want to start going down a set of these. So a first question in sort of the category of understanding pH and POH is looking at how to do a calculation. So this particular calculation is giving you a concentration of the hydroxide ion. So let's write that down. 2.8 times 10 to the minus 7 molar. We are told that our temperature is 25 degrees C, and we need to find the hydronium ion concentration. And specifically, the question in Newton was, why on earth are we being told what the temperature is? Does anybody have a suggestion about that detail, why we need to know the temperature for this particular calculation? Yes?
That tells us kW.
That tells us kW, that's right. So remember that the autoionization of water, which is this reaction here, has an equilibrium constant that we call Kw, and at 25 degrees C, that value for Kw is 10 to the minus 14 molar squared. So this is the fact that determines a lot of things that we do with acids and bases. This is how we know that neutral water has a pH of 7 and neutral water has a POH of 7. This is the fact that we use to calculate the hydronium ion concentration in this particular calculation. So we take our 10 to the minus 14 molar squared, and that is going to equal our concentration of hydroxide ion times our concentration of hydronium ion. We have that number, the hydroxide ion, so we simply divide it through. And so H3O plus is going to equal 10 to the minus 14 molar squared over 2.8 times 10 to the minus 7 molar. And I'm going to assume that you can plug that into your calculator to get your value for the concentration of the hydronium ion. So the 25 degrees itself does not become part of the calculation. It is simply acknowledging that the value that we have memorized for the equilibrium constant for the autodissociation of water is the right one to be using. If you ever see something that is happening at something other than 25 degrees C, then you need to go look up what that equilibrium constant is under those conditions. That is not something you should either expect to have to calculate or something you should expect to know. You would have to go look it up somewhere. Okay. Are there any questions on that kind of calculation and the role of temperature in pH, POH? Okay. There's a general question that's related that came up saying that temperature can change the pH of a substance and asking the question, is this change consistent across all substances and what's causing the change? So the pH can be affected by a variety of things. Kw is one of them. You can also have an equilibrium constant with a Ka or a Kb that's associated with a weak acid or a weak base. All equilibrium constants have some delta H associated with them, have some enthalpy change associated with them. And because of that, from what we learned for the last exam about Le Chatelier's principle, when you change the temperature, you are going to change the equilibrium constant in response to that. And how much does that equilibrium constant change? It depends on the specific reaction you're looking at. This is not something that you can say there will be some sort of consistent magnitude of change that you'll have for the pH with temperature. You can't even necessarily say which direction it is always going to be. So yes, the pH changes with temperature. The change is not consistent across substances, and the cause of the change is simply that equilibrium constants are temperature dependent, and that's about as far as we can go at this point. Any questions on temperature as it relates to pH and POH and such? Okay. There was some confusion expressed about finding the pH of a strong base such as this. And this comes down to a question of stoichiometry. So it is very tempting to write concentrations of things without including what is the concentration of. And let me show you why that's a particular problem here. If we look at this and say that our concentration of our base is 1.35 times 10 to the minus 5 molar. Well, it's a base, and so it's a strong base, so it makes so it fully dissociates to make OHs, and so it might be tempting to say that this is going to be our concentration of hydroxide, and so we then find our POH as 10 to the minus, as the negative log base 10 of 1.35 times 10 to the minus 5. And what we get when we do that, get my calculator up. So 1.35 times 10 to the minus 5, and we get and we do log base 10 of that, and we would find a POH of 4.87. The problem with this is that we didn't identify what our species was that this is the concentration for. What we actually have is 1.35 times 10 to the minus 5 molar of CaOH2. And what we need is the concentration of OH minus. And what we can tell from the stoichiometry of the reaction, CaOH2 is in equilibrium with, actually it's not an equilibrium, it's because this is a strong base, Ca2 plus aqueous plus 2 OH minus aqueous. Right? Because there are two OHs that are part of this compound. So we need to have a stoichiometric conversion factor, 1 mole of CaOH2 for 2 moles of OH minus. Okay. And since molarity is moles per liter, we're just leaving the liter portion unchanged. And so we now find that this is 2.70 times 10 to the minus 5 molar in OH minus. And so our POH is going to be the negative log base 10 of that, 2.70 times 10 to the minus 5, which is 2.7 times 10 to the minus 5. Take the log base 10 of that, and we find our pH is POH is 4.57 rather than 4.87. Okay. Now, so it's important to keep track of what it is you are taking the concentration of. This right here is part of the unit you are using. And it is the way to avoid problems is to keep your units as explicit as possible. A related question here was somebody that was getting confused because they'd noticed a pattern in doing some kind of calculations, and sometimes you subtract your answer from 14 to get your answer, and sometimes you don't, and wasn't able to determine when you do that and when you don't. That's why you need to label things very carefully here. So we just now determined the POH of this particular solution, but the problem is saying that we are wanting to know the pH. And our relationship between those two things is that pH plus POH equals 14. So that means if we want the pH, it's 14 minus the POH. And so then we are going to take 14 minus this value, which is going to be 9.43, I believe, if I did the math in my head correctly. So it's not that you always subtract from 14 or you don't, it's that you keep track of what it is you calculated. If what you calculated was the POH and it's asking for pH, yes, you subtract it from 14. Contrariwise, if you got the pH and you need the POH, same thing. But you just have to keep track of what you're dealing with. Any questions on any of these kinds of calculations? A lot of this was in the practice for last week's homework, so that's one reason I'm going through these particular questions relatively quickly. But I'm happy to slow down if anybody has confusions. Okay. All right, there's a general question. How can you tell if a substance is amphiprotic or not? So the main thing to do would be to figure out what its acid reaction would look like and what its base reaction would look like, and see, do the products that come from that make sense or not? So, for example, let's look at ammonia, NH3. Its acid reaction, where it is acting like acting as an acid, would be donating a proton to water. Okay. Its base reaction would be accepting a proton from water. And so what you do is you look at these potential products, the NH2 minus and the NH4 plus, and say, is it actually reasonable under some conditions for these things to form? And in this particular case, we know that this one can form. We know that the NH4 plus can form because you have seen the ammonium ion before. This one is a little less clear as to whether that one is going to form. It's not generally going to form in water, but there may be some other contexts in which you could have the NH2 minus ion. If you're not reacting with water, for example, maybe you are reacting with an OCH3 minus ion. So a methoxy ion, which is a very, very strong base, and so might be able to pull a hydrogen off in this way. So, but let's contrast this with something like methane. So CH4 plus H2O, if it's acting as an acid, could form CH3 minus plus H2O. If it acts as a base, CH4 plus H2O would react to form CH5 plus H2O. Not H2O, sorry, this is H3O plus and this is OH minus. Now, this one is similar to this one up here in that while water is very unlikely to do this, there might be something that would be acidic enough to pull off an H plus from this. And so it's in an aqueous system, it's not going to act as an acid, but in some other context, it might if you have a strong enough base that you're interacting with. But this reaction down here makes no sense at all because CH5 plus, what would its Lewis structure look like? Well, if we are forming 5 bonds to hydrogens, if you count up the electrons here, you have too many electrons. And you've exceeded the octet of the carbon. So this isn't, this reaction is completely nonsensical here. And so methane is impossible to be amphiprotic. So the general process is think about what the result of an acid reaction would be and what the result of a base reaction would be. And then look at those products and say, do they make chemical sense or not? Okay. All right. Some questions about stepwise ionization. And so this is getting at something like polyprotic acids. Let's look at an example, say phosphoric acid. We can imagine one of the hydrogens acting as an acid. We can imagine the second one also acting as an acid. And we can imagine the third one also acting as an acid. Nope, 2 minus. This is stepwise ionization, where sequentially multiple H pluses can act as acids in the system. Each of these will have a different acid constant, so that you'll have a Ka1, a Ka2, and a Ka3. In most cases, these Ks are going to be quite different from each other, sometimes as much as a factor of 10 to the 4th difference between them. And what that means is that at some pH, only one of these equilibria will be active, will be such that there's a reasonable amount of both sides in it. This, in fact, is going to be one of the examples that's going to be looked at in the small group activity you're about to do. And you're going to be given the Kas for each of these reactions. And you're going to be looking at it in the pH range of blood and figuring out which of these equilibria is the one that is important, is active at that point, and you'll then be calculating. So let's pretend the middle one is the one that's active. What that would mean is that there's a reasonable concentration of the dihydrogen phosphate here and a reasonable concentration of the hydrogen phosphate. But then if you go up and calculate how much of the phosphoric acid with 3 hydrogens in it, it'll be absolutely tiny. And if you calculate how much of the phosphate ion there is, that also will be absolutely tiny. So you only have a little bit, you only have some of these two, and these are negligible, is the idea. So that's the idea of a stepwise ionization. Any clarifying questions on that? Okay. Sounds like there was also some continued confusion about conjugate acids and bases, what they are, when we need to care about them, and that sort of thing. A question in the chat, going back to the previous question. How do you find out if you have reasonable concentrations? Okay, so if you have the equilibrium constant here, and then you're given one of these two concentrations and then the hydronium ion concentration by being told what the pH is, you can calculate what the other concentration of the two is. Just by using the equilibrium constant expression for the acid constant you have. Once you get those numbers, you can then do exactly the same calculation here because you've just figured out what this concentration is. It's the same species, and you have the pH, and you have the Ka, so you can calculate this one. And then you would find that if this one is like 5 orders of magnitude smaller than this, then it's a negligible amount that you have. All right, so conjugate acids and bases. What are they? Why do we care? What are we going to do with them? So the general idea for an acid reaction is that we write our standard acid reaction down. So HA, aqueous, plus H2O, liquid, equilibrium with A minus, aqueous, and H3O plus, aqueous. So the way to think about this reaction is that it is a proton transfer. The things on the right are the same as the things on the left, except a proton has been exchanged from one compound to the other. So what we do is we think of this A minus thing as existing in two states. One state has the proton on it, the other state does not have the proton on it, but it's essentially the same thing. It just is in two different states. So because it's basically the same thing, this is a pair that you will always find in an acid-base reaction involving this species. This side, we see that it is acting as an acid. This one, if it is reacting and going the other way, we see that this is going to be the acceptor of the proton, so it is acting as a base. And because these are linked by being the same substance, just with or without the proton, we call them a conjugate pair. So if we say that HA is an acid, then A minus is its conjugate base. Similarly, we have a water molecule here that can have an added proton onto it. So those also form a conjugate pair. Here, the water is acting as a base, and the hydronium in the reverse reaction would be acting as an acid. So in this reaction, water is a base, and its conjugate acid is the hydronium ion. So that's how we identify conjugate pairs. Why do we care? Well, the biggest place we use this, we actually use it kind of in two different cases, but the biggest place we use it is in buffers. Whenever we have a buffer, we have a reaction like this happening, and we want to start off with close to the same amount of the acid and its conjugate base in solution. And so identifying what the conjugate of a particular acid is lets you know what the thing is you need to add to the sample in order to make it into a buffer. So if you're dealing with acetic acid, CH3COOH, then you can look at this and say, what does it look like missing its hydrogen? Well, that would be the acetate ion, CH3COO minus. And so those are the conjugate pair that we would use to make an acetate buffer. And so this we can just put in as it is. This one, we have to have some kind of counter ion we would use with it, so that, because you can't just have a bottle of negatively charged ions. There have to be positively charged counter ions to work with it. So you could make sodium acetate, and you are therefore able to add the acetate ion into the system without it starting out in its protonated form. Okay. One thing you can notice here as well, why did I pick sodium? Well, I picked sodium because sodium is the conjugate acid of a strong base. So NaOH forms Na plus OH minus, right? But I only drew the arrow one direction because the sodium ion is not going to grab any hydroxides out of water to form solid sodium hydroxide. This is a single direction. And so we know that putting the sodium ion into this solution, it's not going to interfere with any of the acid-base chemistry that we're doing. The sodium ion will be what's known as a spectator ion, which I think you may have heard about before back in the section in Chem 111 on double displacement reactions. So it's the same idea here, is that you identify the counter ion to use as something that is not going to be acid or base active at all. And sodium's a good choice for that. Okay, so this is how you do this for an acid reaction. Suppose you're starting with a base though. So the standard base reaction is our base plus H2O is in equilibrium with BH minus plus OH minus, BH plus, excuse me, and plus OH minus aqueous. And so once again, we have a substance that is acting acting as though it has two states, either with the proton or without the proton. And so that substance forms a conjugate pair. The B here is acting as a base. In the reverse reaction, the BH plus is acting as an acid because it is donating its proton to the other species. And so the conjugate acid of base B is BH plus. Similarly, we have the water and hydroxide forming a conjugate pair, where the water is acting as an acid in this case, and its conjugate base is the hydroxide ion. All right, okay, so I said that there were two main places where we use the idea of conjugates. One of them is to know how to make a buffer system, what it is we need to mix together to make that buffer system. The second is to understand the acid-base behavior of salts. So I was mentioning here the NaCH3COO species. This is an ionic compound that you can get as I think it's a white powder that you could then dissolve into water. And the question then would be, what would the pH be if we just took that, put it into water? Is it going to make it acidic? Is it going to make it basic? Is it going to do nothing? Well, we have this reaction up here going on. So if we add in the acetate, which is this species here, the A-, then, and we don't start with any of the HA acid, the acetic acid, so we just put in the A-, then the equilibrium has to shift from products to reactants, has to shift from right to left. And so that is going to decrease the amount of acid that's present, thereby making the solution basic. So if you make a solution with the salt of a conjugate base of a weak acid, you make the solution basic. And you can make the same argument the other way around for the conjugate acid of a weak base. Okay, do we have any questions on conjugates? Why we care, what we do with them, how we identify them? Yes?
Could you have used lithium instead of sodium?
Yes, absolutely. We could have used lithium instead of sodium. We could use potassium as well. The reason I tend to pick lithium, sodium, and potassium rather than things like magnesium, cesium, and strontium is that we tend to have higher solubilities with the 1+ than we do with the 2+ ones. And so when we're talking about the acid-base behavior from the perspective of wanting to get a lot of the buffer material into solution, you want to get as much into solution as you possibly can. And so going with the singly charged ions tends to help with that. Okay, so let's see. Very straightforward question. Somebody asked, do we need to memorize the strong acids and bases? I don't tend to ask you to memorize too many things because I know you can just look them up, and I don't have a problem with that. There are lots of things that I don't have memorized that in previous generations people would have had memorized. But there are some particular acids that are used so much that it's useful to know that they are strong. Same thing for some of the bases. And I don't think that all 6 that are listed in the textbook are really absolutely necessary to memorize because only about 3 of them are. I'm going to pull that up here. I'm going to come back. I'll switch to PC and I'm going to share screen. I'm in the wrong place. Here we go. So if we go to the textbook, come down to acids and bases, relative strengths of acids and bases. So here we go. So this chart right here that lists the 6 common strong acids and the 6 common strong bases. I would actually reduce this to 3 and 3 in terms of the ones that I think you ought to have memorized. Hydrochloric acid, I would have memorized, nitric acid, and sulfuric acid. Those are the 3 acids that are used in the laboratory as strong acids much more commonly than anything else. I've done a lot of scientific research in my own lab, and of the others, the only one I have ever used is perchloric acid, which is pretty nasty stuff to work with. Otherwise, everything I have done has been with hydrochloric, nitric, and sulfuric acids, if I wanted a strong acid. On the strong base side, lithium, sodium, and potassium hydroxide are the three that I would remember of those, because they are, again, simply the most common. If you need a base and you need it to be a strong base, those are the ones you grab. And part of that is that the solubilities of these three, I believe, are higher than the solubilities of the calcium, strontium, and barium ones. They're just as strong, but if you can't get as much in there, you can't get to as high a pH. So you have a lot more flexibility in the reactions you're designing using lithium, sodium, and potassium. So in terms of memorizing things, I'm not telling you you have to memorize these things. You should know where this list is so that you can get to it should you see an acid or a base and need to know if it's strong or weak. But memorizing the three that I just identified in each column will speed up your working with problems, because you'll immediately know that they're strong and you'll know what to do with them as a result. Okay, any questions on that? Okay, all right. We did that, all right. Is Kb, so now talking about the acid and base dissociation constants, Ka and Kb. So is Kb only associated with strong bases? I would actually say it's more associated with weak bases. So when you have a strong acid or a strong base, that means that in water at least, you're dealing with the reaction going to completion and the reverse reaction happening effectively not at all. And so that you can think of that as there being a ridiculously high equilibrium constant, but it's never going to be a number that you're going to use. You're just going to say that it all goes to products. The K values, K's mean equilibrium constant. And so if you have an equilibrium, then that means it's weak in that context. Any questions on that? Okay. Somebody wanted me to do an example problem where you are trying to find the Kb rather than using the Kb as the input to the problem. And so in this case, we are looking at a pH of a base of 11.65, an initial concentration of our base is going to be 0.033 molar, and we want to know the Kb. Okay. So the first thing to do with any problem of this type is to write down what our base reaction is. So base plus water in equilibrium with BH plus and OH minus. Okay. Have an initial concentration of 0.033, 0, 0, and minus x, x, x. We don't yet know if this is going to be negligible, but notice here that we end up with x's in these places. So 0.033 minus x. So what we can do now is take our pH and determine what our OH concentration is. So one of the easiest ways to do this is to remember that pH plus POH equals 14. So that says that our POH is going to be, let's see what, 2.35. Getting out of the P scale, our concentration of OH minus is going to be 10 to the minus 2.35 molar. So we'll go into our calculator. 2.35, change sign, 10 to the x. And so that is going to be 0.0045 molar. And so we now can see that we have enough information to get the three concentrations we need to find the Kb. So Kb is going to be the products, BH plus, OH minus, over our reactant, concentration of B. And so it's going to be 0.0045 molar squared over 0.033 minus 0.0045 molar. And so, lose my pen. So 0.0045 squared divided by, I'm going to open parentheses, 0.033 minus 0.0045, close parentheses, equals, and we get 7.11 times 10 to the negative 1, 2, 3, 4. And our units here, we have molar squared in the numerator, a single molar in the denominator, so units of molar. Okay. So that is how we would go about finding a Kb from concentration and pH information. General procedure here makes some sense? Please move it up, yes. So some skills that need to be tools in your toolbox that you just know how to apply and when to apply it. You need to be able to write down your standard base reaction without even really pausing to think about it. Same thing for a standard acid reaction if you have acid going on. You need to know the relationship between pH and pOH, or the relationship between concentration of hydroxide and concentration of hydronium. You need to know how to get into and out of the P scales, pH, pOH, pKa, pKb. You need to know how to write down an equilibrium constant from a reaction. What the expression is, what concentrations you put where. Those tools are essentially all the tools you're going to use for any acid-base problem. We add in a couple more tools when we get to buffers with the Henderson-Hasselbalch equation in particular. Although honestly, that's just a rearrangement of this right here. But almost all acid-base questions are just different combinations of using those tools I just listed. Any clarification on this one? Okay, we're doing on time. All right, quite a bit. All right, we did that. All right, metal hydrates. Why are the water molecules attached to a metal in a hydrate more acidic than normal water? That's a fantastic question. So let's review very briefly what we mean by a metal hydrate. And so I'm going to use the aluminum 3+ example. What happens is that we have water molecules where they end up donating in a Lewis acid base kind of way a pair of electrons from the water to the ion to form a coordination complex, so that we can draw this as that. And actually, we would probably put a little bracket up here and say 3+. And we can have more than, let me back up for just a second because a question came in to the chat. Can you please repeat the tools we need to know? Certainly. Actually, why don't I list them just to make sure. So put a pin in this, we're going to come right back to it. So tools you need to know for acid-base problems. You need to be able to write the standard acid reaction or base reaction for any acid or base. And remember, in the Bronsted-Lowry definition, it's simply being a proton donor or a proton acceptor. So there's nothing special or magical about these reactions. It's just you take your acid and you remove an H+, and that becomes the conjugate base that's on the other side. If you're starting with the base, you add an H+, and that then becomes your conjugate acid that's on the other side. Secondly, you need to know the relationship between pH and pOH, or the relationship between concentration of OH minus and concentration of hydronium ions. You need to know how to get into and out of P scales. You need to know how to write the equilibrium constant expression for any equilibrium. That's pretty much it. And you could add how to run an ice table into this list if you want. But honestly, when you think about what an ice table is, it's really just a way to keep track of how the reaction changes due to stoichiometry to use the equilibrium constant expression. So any acid-base problem you can solve with this set of information. All right. I'm now going to switch back over here. So let me refresh our memory on what I was starting to say. We have a metal ion that we've placed into water. The metal ion is electron deficient, meaning that it has a positive charge on it, having lost its electrons. An electron deficient species that is in water is surrounded by lone pairs of electrons on the oxygens in the water. And so the lone pairs can donate in a Lewis acid-base fashion to the metal ion to form a bond. And this will typically happen with a bunch of water molecules that are surrounding that central metal ion. So aluminum, for example, will typically have 6 water molecules that get associated with it. Now, let's compare the acidity of a standard water molecule and a water molecule that has the aluminum ion attached to it. In both cases, when these act as acids, what happens is that these electrons get pulled back onto the oxygen, resulting in the top case, an HO minus, in the bottom case, an HOAl. This is going to have a 2+ on the whole thing. And they'll each have the H+ that has come off and then probably attached to something else. All right, so that's what's This is the process that's going on when each of these two species that we're comparing acts as a Bronsted-Lowry acid. So the question then becomes, in which case are the electrons already pulled towards the oxygen more when you're starting? And the fact that the aluminum that it's attached to is positively charged means that that aluminum is pulling electron density down towards it from the oxygen, right? It's not very electronegative, so we can't really describe it as the electrons getting transferred to it, but it is a positive charge. And so electrons are attracted to positive charges. And so because of that, in the bottom case here, the bond to that hydrogen is already weakened because the electron density is being shifted towards the metal ion. That makes it easier for the hydrogen to come off, making this species more acidic than water by itself. Does that general idea make some sense? Yeah. This is the same kind of argument we used Monday and Tuesday when we were talking about finding the oxidation numbers for central atoms in oxyacids to explain, for example, the difference in acidity between sulfuric acid and sulfurous acid, or nitric acid and nitrous acid. So it's the same idea. If the electrons are being pulled away from the hydrogen because there's more positive charge at the center of whatever you're dealing with, then those hydrogens become more acidic. Any clarifying questions on that? Okay. All right. Why do charge and ionic size affect the acidity of a metal hydrate? Well, because the larger, let's talk about charge first. So if we compare an aluminum 3+ to maybe a zinc 2+, the aluminum 3+, because it has a higher positive charge, is going to be pulling the electrons in more tightly. And so it would make sense that the higher the charge, the more acidic the hydrate is going to end up being. Now, how about atomic size? So comparing aluminum 3+ to gallium 3+, which is directly below it on the periodic table. Gallium is larger than aluminum. Well, so the smaller the ion is, the more concentrated that positive charge is that you're dealing with. And so the more it's going to be pulling those electrons in towards itself. So same general argument. Any clarifying questions on that? Okay. Okay, how do you know which mixtures will result in a neutral solution? So this is something that the textbook spends an inordinate amount of time talking about, and there are apparently a lot of Newton questions on this as well. And I think that's really silly because I don't think these questions are particularly useful. Because it gives you the impression that if you take a strong acid and a strong base and you mix them together, you will get a neutral solution. That it flat out states that, right? But what if your base solution is more concentrated than your acid solution? It's not going to end up neutral, right? What if you're dealing with a diprotic strong acid like sulfuric acid and a base that only produces one hydroxide ion? You're not going to get a neutral solution in that situation. So I think all of these, this whole list of weak acid with strong base, strong acid with weak base, weak acid with weak base, it's trying to catalog all of that is just misguided. What you really need to do is think about strong acids and strong bases as dissociating completely. Think of weak acids and weak bases as being in equilibrium, and that's enough. That's what you use to figure out what the result is going to be. And so I wish that Newton and the textbook didn't do what they do because it gives incorrect perceptions. So I'm gonna leave that one at that right here. Okay. Okay, so there were some questions about Lewis acids and bases. So are acid ionization constants and base ionization constants only related to Bronsted-Lowry, or can they relate to Lewis? So the way we have formulated the standard acid reaction and the standard base reaction is in terms of a Bronsted-Lowry reaction. So here's the standard acid reaction we were talking about, and we have a similar standard base reaction right here. And those are depicted in terms of a Bronsted-Lowry proton exchange process. I have never seen so Bronsted-Lowry reactions can be depicted as a Lewis acid-base reaction because there is still the formation of the oxygen-hydrogen bond here, where the oxygen from water is donating a pair of electrons to the hydrogen that it's pulling off. So you can talk about this as a Lewis acid-base reaction. So in that sense, you could have these, you could think of these as a Lewis acid-base reaction, and the Kas and the Kbs could be related to those reactions. I have never seen Ka and Kb used for a Lewis acid-base reaction that was not also a Bronsted-Lowry acid-base reaction. So cases like, I mean, we just talked about the aluminum 3+, where we have the water molecules coming in, forming a covalent bond, and I described that as a Lewis acid-base reaction, which it is. You're forming a coordinate complex by doing this. This is not a Bronsted-Lowry acid-base reaction, but I have never seen anything like this described with a Ka or Kb. There will be an equilibrium constant associated with it, but the special designations of the A and the B here, in my experience, have been completely limited to Bronsted-Lowry. Coordinate complexes. Okay, so there are one problem with the coordinate complexes is that I have come across two very different definitions for them. And it's not clear to me that the textbook and Newton are being particularly clear about them. The first one that I came across when I was preparing for this class was that a coordinate complex is the result of a Lewis acid-base reaction. So this would imply that anything where a lone pair of electrons is donated to some Lewis acid to form a covalent bond, this would then be considered to be a coordinate complex by that definition. I have also seen a definition that limits this further, such that the thing being donated to has to be a metal ion. And that is where, prior to teaching this class, I have seen it used more often because you talk about coordination complexes a lot in inorganic chemistry, where you deal with metal centers and then various ligands that are attached to the outside of that metal center, similar to the water molecules in the metal hydrates we were just talking about. I have not seen outside of this particular class, I have not seen cases of a covalent bond being formed by a Lewis acid-base reaction where it's not a metal being called a coordination complex. However, the definition in the textbook, I believe, doesn't do that limitation. I'm not 100% sure of that, but either that or in Newton somewhere, it doesn't have the limitation of the metal. So I think from a practical standpoint moving forward in chemistry, you should probably consider it to be restricted to cases where it is a metal that is acting as the Lewis acid in these cases. In terms of Newton, I think we may have to dig a little further to see which way it is asking those questions. I will not be asking you to define things on an exam as a coordinate complex one way or the other, because we're not really talking about Lewis acids and bases very much in the first place. And it's the distinction about why metals do this and why other things don't isn't really something that becomes important until you get into an inorganic chemistry course several years down the line. So I'm not going to be emphasizing this strongly one way or the other. So does that help? All right. Okay. I'm not sure why I put this one under Lewis acids and bases. pH drinking water. So in just the last couple of minutes, I want to talk very briefly about the pH of water, because there are some misconceptions that we've built up here about the pH of water that we need to think about a little bit. And the reason that there's some misconceptions about it have to do with carbon dioxide. Our atmosphere has carbon dioxide in it. And from Henry's law, we know that gases will dissolve into water. The problem is that carbon dioxide, when it dissolves with water, forms carbonic acid, which is a diprotic acid. So H2CO3 plus H2O will form HCO3 minus plus H3O plus. And so that's the bicarbonate ion here. And HCO3 minus plus H2O is in equilibrium with the carbonate ion, CO3 2 minus plus H3O plus. So get yourself some pure distilled water, leave it out open to the air, and you measure its pH. It is not going to be 7. It is going to be acidic, because this is what's going on just naturally because of the carbon dioxide in the air, which equilibrates with carbonic acid, which equilibrates with bicarbonate, which equilibrates with carbonate. So very naturally, water is acidic in a standard environment, in a standard open to the air environment. However, drinking water is generally pH balanced by the people who are supplying the water to you. So drinking water usually has minerals added to it, which will render the water slightly basic. So tap water tends to be at something around, I think, about a 7.5 pH that you have. So it's important to keep these ideas in mind when you're doing pH studies on something, because the information that's sort of been drilled into your head, neutral water has pH of 7, is ignoring some of the realities of working with the water we have available. So if you get good distilled water, it won't have all those minerals in it. But to avoid the CO2 problem, you also have to keep your water away from any environmental source of CO2. You have to have it in a sealed container. Maybe you put a blanket of nitrogen gas over it or something like that to deal with. Okay, so I have run us out of time. We have not quite gotten through all of the muddiest point questions that we had. So these will be top of the list for tomorrow, and you'll be able to, if you're not going to attend tomorrow's class, which is perfectly fine, you'll be able to access those in the video and it'll be timestamped. So in particular, things to look for is some details on how to do some of these calculations. When do you know if you can neglect X in the ice tables or neglect the initial concentration of hydronium or hydroxide? Dealing with weird units like this, the molar to the fifth, something like that, that shows up in equilibrium constants. When do you use ice tables and when you don't? How do you combine the ideas of equilibrium with a limiting reagent? And then some clarifications on a buffer system. So what is it? What is a buffer system? Which species can form a buffer system? We talked about that a little bit already with the weak acid and its conjugate base. That's essentially the idea. And then finally, how do you actually use the Henderson-Hasselbalch equation that we derived in the first couple days this week for a real problem that we might try to solve? And there is a couple of details to that, to making that work well. And I understand from the Piazza questions that the Newton explanations were somewhat lacking in that regard. So I will definitely go over that as well. Thank you very much. And I will be on the lookout for the small group activity this afternoon.